Okay, so let's, a lot of you guys, raise your hand if you were here when we talked about work and energy
Yes.
last week. We've been before, like Wednesday-ish, Thursday-ish.
Oh, was that the cookie?
And then I went home and made cookies.
Nice, see, that was all me.
From against the wall.
Yeah, they lasted a night.
I want you to know over the weekend I did try that.
I made cookies too.
You did try that? You'd have to go pretty fast. We'll do a calculation. Okay, so anyway, let's, for those that were gone and for those that were here, let's kind of rehash this a little bit. We'll summarize it. So we added a few new quantities, and this is really the nice thing about this. Let me just reiterate that this makes physics a lot easier. There's a lot of problems you can now solve without having to do a bunch of vector analysis, which I know we all love, but it's a much more elegant way to do physics. The math gets a lot easier. You can't solve every problem this way, but you can solve a lot of them. Okay, and there's some problems that we couldn't have done before that we now can do. Okay, so we defined some new quantities. Kinetic energy. What does kinetic mean? Movement, right? Speaking of movement, once you move that there, you're perfect. Excellent. That's a movement. So kinetic energy is the energy of motion, right? Kinetic energy, we call that capital K, and it equals 1/2, whoops, not 1/2, not 1/m, 1/2 mv squared. But what do you notice about that v?
It's squared.
It's squared. What else do you notice about it?
It's lowercase.
It's lowercase. What else is it
No
missing?
vector.
It's not a vector.
Oh.
Okay, so it's independent of direction, right? It's 1/2 times 1/2 m v squared, where v stands for speed, right? It only has to do with the mass and the speed of an object, right? Okay, so kinetic energy is proportional to mass. So if I double the mass of something, its kinetic energy doubles, but it's proportional to speed squared, right? That's interesting. Now we talked about, well, okay, we'll get back to that, right? So if I double the speed, what does that do to the kinetic energy? It increases it by a factor of
Wait, you double the speed?
4, because I'm squaring it, right? If I triple the speed, I'm increasing kinetic energy by a factor of 9, okay? What about gravitational potential energy? We call that P. And what's that equal to? Do you remember? This one equaled mass times the acceleration of gravity times the amount times h. Oh, we're already adding these up there. Excellent. You need some pens. You want a black one too? You got to make this fancy, don't you? Let's see.
What was that blue?
What was that guy?
Is there not a black one over there?
No,
Oh, man.
there's just 2 red ones.
Just 2 red ones. That's not going to do the job.
Yeah, they're not in here.
Oh, here we go.
But the title will be.
This will be, the title of the whole thing will be Work and Energy. Excellent. Okay, so H. Now H is going to be the distance, the height above or below whatever our reference is going to be for gravitational potential energy. Because to say that there's some absolute gravitational potential energy is kind of ridiculous, right? It's only, like we would say, for example, we're going to go through some examples here in the room, and we'll pick a reasonable, yeah, we'll pick a reasonable reference. What's that?
Zero.
Yeah, it's, well, depends if that's before or after he falls off the deck. So we'll pick a reference value that makes sense. Okay, so we'll get back to that, MGH. Now, what about work? Work is the one that we spent the most time on, and that's the one that's just a little bit harder to wrap your head around. It's not bad. What was that equal to? Remember? A couple ways we can think about this.
No, I'm not even gonna try. I was awake for that.
You were awake for
I
that?
don't remember that.
Okay, we said work was equal to, it had something to do with the product of force and displacement, right? So force through a distance, right? But we had to be a little more specific. We could either say it was the parallel component of force times the displacement. So that the component of force in the direction of displacement, or if we wanted to, we could think of that as force times the component of displacement along the lines of force. Or, even better than that, we ended up with the formula, okay, there you go, that's convenient. F d cosine theta, where theta is the angle between the displacement and the line of force, right? And so we looked at some examples. We took an example like, let's just say I've got this 1 kilogram object here. If I take this 1 kilogram object and I'm going to, let's say I'm going to, let me do some work on this thing. I'm going to push it on a frictionless surface. I'm going to push it with a force of 10 newtons through a distance of 2 meters. Okay? How much work did I do?
10 newtons for 2 meters.
20.
200.
10 newtons for 2 meters, 20 joules, right? I did 20, because that would be, what's theta in that case?
Theta?
Yeah, if
Yeah, 180.
the direction of displacement is that way and the push is that way, aren't they same direction, right? Okay, make sense? So that would just give us,
So theta would be 0 then?
say that again?
So theta would be 0 then, since they're both.
Theta is 0, exactly. And what's the cosine of 0?
0.
No.
No, 1.
1. Okay, so that would give us 10 newtons times 2 meters, which is 20 newton meters, but the units for energy or work are joules. Okay, and that's the symbol for, that's how you spell it.
Joule? Joule?
What's that? You don't probably need that one up there, the units. Okay, good. There'll be a couple more. I'll call you up here maybe 1 or 2 times.
Oh!
Oh my god. Ah.
Yeah, honestly, that was impressive. You were maybe moving like.
Oh.
That worked the stairs too.
Seriously, she just walks out.
Yeah, anyway.
I don't even get it. She's
Like she
moving
came
like
it.
that slow.
All right, so what about this one? What if an object was sliding along on a frictionless surface, and to slow it down, I'm going to apply a force of 20 newtons through a distance of 2 meters. That's how long it takes me to have it come to rest. Okay? How much work did I do there?
Wait, can you?
So I'm pushing this direction, the object is sliding towards me, and I'm going to push on it with a force of 20 newtons, and I have to push, it travels 2 meters while I'm pushing before I can finally bring it to rest.
Work can't be negative, can it?
It can be,
Oh, okay.
it can be. So what is that work going to be?
Negative.
Okay, it's going to be negative 40. How come? Because there's a couple ways we can look at this. If we don't want to mess with the angle, which we don't really have to, because the forces are all acting on the same line here, right? So if the line is, let's just say let's call this the positive direction and this is the negative direction, right? So if the object, then let's say it was going this way. It was moving in the positive direction and I pushed on it in the negative direction, right? So the force that I applied was in this direction, right? But the displacement was in this direction. So that makes it negative because the component of force is in the opposite direction of the displacement, right? In terms of theta, what would that look like? There's the force vector, right? There's the displacement vector. What's the angle between the two? 180. Everybody see that? So that's force, that's displacement, and the angle between them is 180. What's the cosine of 180?
1.
No.
0.
No, what's the cosine of 180?
Cosine.
Think,
-1. -0.
that's -1. Think unit circle, right? This is 180 degrees. Cosine is the x-coordinate. What's the x-coordinate on the unit circle there?
Negative 1.
Yeah, the coordinates are negative 1, 0, right? Okay, so yeah, it's doing negative work, right? Okay, well, turns out that kinetic energy and work are linked, right? The net work done on an object by a force is equal to the change in kinetic energy, right? So does that make sense? By all the forces, the net work that's done is the change in kinetic energy. So the first example, if this is on a frictionless surface, the only force acting is my push on the object. Well, there's another force acting too, though. It's gravity, right? Is gravity doing any work? If this is just sliding along on a frictionless surface,
It's not,
how come?
because it's not moving yet.
Okay, it's not moving
It's not
it.
directional.
Voicemail.
Okay.
It's a voicemail, guys.
Yeah.
Hey, Gary. Yep. 304. Rarely.
She's like, did you type?
That's the lab. Yeah, we're usually over here. Yeah. Before 2, gotcha. And go to the office or what? Okay. Bye.
Got some freaky going on?
Yeah, you gotta leave it before 2.
Yeah.
Go sign out. You know what it's for, probably.
Yeah.
Okay.
When?
Huh?
Right now?
A little before 2.
Oh, okay.
Yeah, not now.
Oh.
Not now.
Yeah, man.
You still got some nap time, it's fine.
Yeah.
So,
Awesome.
okay, so, yeah, well, how come gravity's doing no work on this thing?
Because it's not directional.
moving it.
Well, no, it is directional. What direction is gravity pointing it? It's towards the
Down.
Okay, what direction is the displacement?
It's not moving it anymore. Negative.
It's true.
Gravity's canceled out at the moment.
Well, in what direction is it moving?
Down.
90 degrees.
What's the angle between those?
90.
What's the cosine of 90?
0.
0, right? There's no component of the gravitational force along the direction of travel, right? It's acting perpendicular to the direction of travel, right? Another way of thinking about it is the displacement, there's no component of the displacement vertically, right? And so it doesn't do any work. Same thing with normal force, right? So this object, if there truly were no friction, right, this object would slide at the same speed forever. Agree?
Yes.
Does that happen in space?
It does. Right. So for example, that's not a great example because even if the Earth were completely frozen over and we could reduce the friction, you're never going to get it quite to 0 on Earth, are you? Right?
No, that's.
You could maybe magnetically levitate it above the surface and evacuate all the air from the planet. That's a lot of work to think about doing that stuff. There's a much easier example where we could do this.
Hollowed out the center.
Well, that's still pretty hard to do. There's a pretty easy, relatively easy example of where we could see this going on though. Space. Yeah, if I just went up, if I went up high enough and I launched this thing horizontally and put it in orbit, right? Then if it's in a perfectly circular orbit, the gravity's doing no work on it, is it? Because the object is always moving. If you think about what that picture would look like. If you think about this picture, here's the orbit. Right, and here's the Earth in the center. Right, and so the object, here's the object, that's the displacement vector at any one moment, right? If we switched off gravity at any moment, wouldn't you agree this object would just fly off tangentially?
Sure.
Right? So that's the direction of displacement. This is the direction of the gravitational force. They're always at right angles, right? And so therefore, gravity does no work on the object, okay? When I pushed on it though, I did some positive work, right? Because I moved it in that direction. What was the result of that? In example 1, the thing was at rest, and I pushed on it with a force of, what was it, 20 newtons for 1 meter or something like that?
No, it was 10
meters.
10 newtons for 2 meters, right? And we said that I gave it 20 joules of kinetic energy.
Right.
Well, the work that I did was invested in that object then in the form of kinetic energy. Agreed? Does that make sense? Okay, what about example number 2? It was flying towards me, and I pushed against it, and it went from having some kinetic energy to rest. So the work that I did, once again, was invested in this object. This time, it removed the kinetic energy, right? So one thing we can say then is the net work done on an object always results in a change in kinetic energy, right? Okay, now let's look at another example here. Let's look at the example where we're gonna take this 1 kilogram object and we're gonna perform another pretty simple experiment here. I'm gonna gradually pick this thing up at constant speed, 1 meter, and set it on a shelf, like we did the other day, right? So what's the work that I'm doing on the object? How much force am I applying?
5 newtons.
The same.
It's got a mass of 1 kilogram.
Kilogram.
So 9.8, roughly 10, let's just say 10, to make the numbers easier, right? So I'm applying a force of 10 newtons to support this thing. It's not accelerating, so I'm just supporting it, right? I put it up on the shelf. How far did I move it?
1 meter.
1 meter, okay? So if I pushed in that direction with a force of 10 newtons and I moved it in that direction 1 meter, how much work did I do? 10 joules. Okay, that's how much work I did. Good. Okay, where did the work go this time though?
Potential.
Okay, it was invested in gravitational potential energy, right? Everybody see that? I got something out of it this time, but it wasn't kinetic energy, it was gravitational potential energy. Here's where this gets a little bit complicated, where you gotta really kind of pay attention to this stuff. Okay, if this equation is true, the net work done on the object must equal change in kinetic energy, but did the kinetic energy change? No, we just moved it up at constant speed, right? And now we're done. It's still moving at that same speed though, right? So there was no change in kinetic energy. So if there's no change in kinetic energy, that would seem to imply that the net work done by all forces on this object is 0. But I did 10 joules. How could it be 0? What other forces are acting on this? What are the forces acting on this object?
Gravity.
Oh, okay, so there's 2 forces, right? There's the normal force, there's my pushing force, we'll just call it that. Right, my hand pushing up. In what direction is gravity pushing? Down. Okay, so with what force is gravity pushing? This has a mass of 1 kilogram. 10 newtons in that direction, and I'm moving it up 1 meter in that direction. So how much work is done by gravity? Negative 10, right? Because the force and the displacement are in opposite directions. So it works, right? There's 2 forces acting. I did positive 10 joules of work and gravity did negative 10 joules of work. And so what's the net work then? 0, right? It's easy to add up work because it's not a vector quantity. It's always just a scalar. Just add the numbers up, right? Positive 10 and negative 10, I get 0. So yeah, that makes sense. The change in kinetic energy should have been 0 because the amount of work done was 0, right? Okay, what if we try something a little different? This time, let's say I'm going to push this thing up with more than 10 joules, or more than 10 newtons. I'm going to push it up with 20 newtons. I'm going to push it up with 20 newtons of force for a distance of 1 meter, okay? So it starts off at rest probably, right? I'm going to accelerate this thing up, and when I get to the level of the shelf, how much work have I done?
10 newtons.
No, I'm pushing with a force of 20 newtons, pushing upward. I've done 20 joules of work. How much work has gravity done? Negative 10, because the force of gravity is just negative 10 newtons, right? And I pushed it up 1 meter. So what's the net work that time?
10.
10, right? So in that case, it's going to be 10. Okay, so how much kinetic energy do you suppose it had when it got up to the level of that shelf?
20 joules.
I did 20. Gravity did negative 10, so the net work was 10. So what's the answer? 10, right? It had a leftover account. In the kinetic energy account, there was a leftover there. There was a balance of 10 joules, right? Because I had done more work on it than gravity did. Everybody agree?
Yeah.
Okay, so then what's going to really happen if I run that movie forward? We stopped it right there, but if I had let go, what would have really happened to the object?
Keep going up.
It would have sailed up in the air and come back down, right? Okay, this is where this gets really cool. And now you start to see how energy is so beneficial. you think about things in terms of energy. What do you suppose the kinetic energy would be when it got back down to the level of the shelf?
0.
10.
It's gonna be 10.
Oh, that sucks.
It's gonna be 10, right? Can you think about why that might be?
Because, you put that 10 into it, that 20 into it, negative 10 gravity. And right here it still has that 10, and then it goes up, it gains more. And then when it comes back to that same spot, it has that same 10.
Okay, so there's something going on here. When I let go of this thing, right, and the only force acting on it now is gravity. There's only one force acting on it. From that point forward, something special is going on. It's the total energy. If we take account of both the kinetic and the potential energy, it's all going to stay the same. Yeah. So as it rises up, it's losing kinetic energy, but what's it gaining? Okay, right. So as it comes back down, it's exchanging that potential for the kinetic energy, right? And it stays equal. Okay, it stays equal because there's a lot of stuff I'm kind of throwing at you, and we'll take a few days to sort all this out. But I want you to kind of see just a big picture of this initially, and then we'll kind of parse through it later. Yeah.
So same thing with the football earlier, where right here,
Yeah.
it's the same as over here.
Exactly, yeah. And the reason for that is because gravity is what we call a conservative force, right? If we take this one step further, we could say that mechanical energy, which we could call capital M, just equals kinetic energy plus gravitational potential energy. A lot of times we'll call that a U in physics, but I'm pretty sure our book calls it a P. Almost positive. Let me just make sure. So I want to do what our book does. In college books, it would call it a U.
I don't know why you're crying about the book.
Oh, they do call it U. That's good. They call it U.
That's what I was thinking.
Just embrace it.
So back here, I want to change that here too. So this is,
I had D is passing.
You have a D?
I got a D plus in this class. Almost a C.
almost, all right. So the total mechanical energy is equal to K plus U. All right, so what I want to do then, if you have a conservative force in the absence of any non-conservative forces, right? Mechanical energy is always conserved. Okay, so. Okay, so what's a conservative force? A conservative force is any force where the amount of work done from point A to point B is independent of the path you take. Okay, so for example, we just saw that, right? We just saw that with the weight right here, right? If I threw this thing up in the air and it left my hand at the level of the shelf, it didn't matter if it was at the shelf right when it left my hand, or if it went up in the air first and then came back down and got to the shelf. In either case, the mechanical energy was the same, right? Same kind of thing you could say, what if you were going to, in outer space? What if you were going to go, let's say we've got this big planet right here, and we've got this big planet right here, and we want to go from this point right here in space, that's us, to this point right there, right? Would it matter if we took this path that kind of went up like this and got sucked on through like that, or if we took this path that went from here out like that to there? Either way, what do you think is going to be true about the speed when you get to this point right here? It's going to be the same. It's going to be the same, right? Okay. If you were orbiting the Earth, it wouldn't matter if you orbited in that direction or if I went off in that direction. When I travel the Earth once around and I get back to this spot, I'm gonna have the same speed, right?
So, are you saying like if you went around it and went down and then up, you wouldn't gain any speed?
No, you wouldn't. You wouldn't, because you'd be potentially gaining some speed here, but as you went away from it, you'd lose a little speed.
But wouldn't you gain speed when you got to the other gravitational pull field?
Well, in the middle, you'd be losing speed right here because you're moving away from, you're closer to this one than you are to that one, if they're the same mass, let's say, right? That would be a pretty complicated math to do, but with energy, if you're dealing with energy, it makes it really simple because we know that gravitational fields, gravity is a conservative force. Gravitational fields are conservative. It doesn't matter how I get from point A to point B, I'm gonna end up with the same speed either way. Think of it, here's another picture you could draw. If you had a frictionless roller coaster. So let's say that we've got 3 possible tracks. We're gonna cruise through, all we know is that when we get to point A on the tracks, my speed is equal to, let's say, 50 meters per second or something, right? So here's path A. Path A, we're gonna go, it's gonna increase some speed even more, and then we're gonna go up and get to this point B up here where it's a little bit slower, right? The other route we could take, here's another route we could take. We just go straight and up a ramp to there, or we could do something like this. We could go up onto a really high hill and come back down a little bit. Would you agree that in the absence of any friction, just kind of think about this, in the absence of any friction, when you get to B, your speed's gonna be the same, right? If I take this path here, I'm gonna pick up speed as I go down, I'm going really fast. Then I have to go up a really big hill, which causes me to lose a lot of that speed. In this case, I'm maintaining my initial speed. It's not as high as it would be down here, but I'm gonna go up a smaller hill and end up at the same point. With this one, I'm gonna lose most of my speed going up to the top of this big hill, but I gain a little bit back at the end, right? Doesn't matter. All 3 of those are gonna give me the same results if there's no friction acting, if the only force acting is gravity, right? What's an example of a non-conservative force, do you think?
Speed's different. Lincoln Johnson.
So a conservative force is one where it makes no difference what path you take. Okay, let's try another experiment. Let's say I'm gonna push this object from here to here, right? What's the force that's resisting me? Friction, okay? So I have to do a certain amount of work to go from there to there, right? Does that make sense? Okay, well, I'm gonna take a different route. Which way did I do more work? That way, because I pushed it against friction the whole way. The whole time I pushed, friction was resisting me, right? So I had to push in the direction of displacement the whole time. Well, I went through all those dipsy-doodles and curlicues there. I traveled a long distance, right? So I'm doing a lot more work. If I just push it this one little bit of distance, I did much less work. So once again, that is not conservative because the amount of work it took me to go from point A to point B varied from path to path, right? Here it did not. The amount of work it took me to go from there to there was it didn't matter. It didn't matter which path I took. Same thing right there. The amount of work that was done was the same regardless, right? Gravity did a certain amount of work on this object because it reduced its speed. Okay, make sense? Okay, you better go. Okay, right? So then, how could we do a problem like, see ya. Okay, how about a problem like this? How about a problem like this? If I want to determine what the height that this object is going to go to, I want you to tell me if there are any here's my question. So here's the beginning. This object is rolling along on a flat surface with a speed of 30 meters per second. It encounters this incline, and the highest point it gets to before it starts to roll down is 30 meters. Okay? I want to know, what happened? Oh, this one first. Okay, this one first. Gets up to 45 meters. I want to know, were there any non-conservative forces acting? How could I tell?
It's still going 30 meters per second.
Well, when it gets to the top, it's going to be at rest, isn't it, for sure? Right? But what would have to be true if there were no non-conservative forces acting? If the only force acting here that did any work was gravity, right? Then what would have to be true at the beginning and the end? What has to be the same?
The start and end.
Say it again.
Like the velocity, you would start like the ball backwards.
Okay, so one thing, that's good. One thing that would have to be true is if the ball were to roll back through here, how fast would it have to be going at that point? 30, okay. Okay, but we're gonna stop it before it rolls back. How could I tell?
Our potential energy would be the same. as our
Ah,
kinetic
okay,
energy at
good.
the bottom.
Because the mechanical energy would have to be conserved, right? If there are no conservative forces acting. So the sum of its kinetic and potential energy would be the same the whole time. We could check that. That's easy to check, right? So what's the kinetic energy down here? So it's, what's the formula for kinetic energy again, remember? 1/2 mv squared. So it's going to be 1/2 times m times 30 squared. 30 squared is what?
900.
900. Half of that is
450.
450. Okay, so down here that would just equal 450 times its mass, whatever that is. What's its potential energy at the bottom?
0.
Okay, it could be 0. It's 0 if we define what level what height is being 0.
0.
The level of the flat plane below, right? That would be convenient. But I could say that that's 0 right there if I want to. It would be kind of weird. But if I did, then what would the height be here? Negative 45, right? See what I'm saying?
See?
Okay, that would work. Or I could say down here is going to be 0, right? And that's fine. Then whatever that height was, that would be its potential energy at the beginning, and its final potential energy would be that much more. You see what I mean when I say it's all relative, though? We have to define where we're going to set potential energy equal to 0. Well, let's make it 0 here. Let's set this equal to 0. So then we end up with U equals 0. So my total mechanical energy is 450 m, right? Okay, what about up here at the top? What's the speed? 0. So the kinetic energy is 0. Okay, what's the gravitational potential energy?
30.
Well, hold on now. What's the formula for gravitational potential energy? So mgh, right? So m times 10 times 45 meters is what? 450 m, right? And so the total then is 450 m up there also. So did any non-conservative forces act? No, they did not. They did not that time, right? Because we know that the total mechanical energy was conserved, so there was no friction. Okay, what about that? Whoops, what about that situation? That time?
Yes, same thing.
Okay, this time the initial mechanical energy was the same, right? The initial mechanical energy, that's the same we had before, so that's 450 m, right? Everybody agree? So, what about up here? What are we going to get? 0 kinetic, and I get mgh, so that's m times 10 times 30, it's only 300 m, right? So the mechanical energy up here is, it's got to be a capital M. So how much energy did we lose to non-conservative forces? We lost 150 times the mass, right? That many joules of energy was lost. Where'd it go, by the way? Yeah, where is it? So what's that do? Where is it?
Heat.
Yeah, it's just dissipated as heat. Exactly. When you ski down a mountain, you start at the top and you're skiing down the mountain or snowboarding down the mountain. Well, you're gaining quite a bit of kinetic energy, right? But you're not gaining, not all of your potential energy is converted to kinetic energy. A lot of it is lost to friction, right? So where does it go? What do you think you'd see if you put on really sensitive heat goggles, infrared goggles, and you looked at the mountain? What would you see?
Tracks.
You'd see tracks. If they were really sensitive, you'd see that wherever the skis had gone, you'd see that the snow had heated up a little bit, right? That's where the energy goes, okay? Okay, so then, let's talk about, how much time we got? 2 minutes is all?
7.
Oh, 7, good, that's enough. Okay, so I've got kids, teenage kids, and so I am concerned about one of the same thing your parents are concerned about, and that's teenage kids driving around. So I'm gonna give you a little, sometimes knowing the physics helps you make good decisions here. Let's look at this for a second. So here's a pretty simple model about stopping. So when you stop on a road, is that a conservative or non-conservative force?
Non-conservative.
Non-conservative. In fact, you're giving up all of your kinetic energy. Let's just say the road is level, right? Like most of them are.
California.
It's level, and you're starting off with a certain amount of kinetic energy, and you're ending up with no kinetic energy, and your height hasn't changed. So yeah, you gave up all the change in mechanical energy was all of your initial kinetic energy, right? So it is non-conservative, and it's friction, isn't it? Friction is what is causing you to stop. Okay, so the work done by friction, when you skid, for example, let's say you lock up your tires and you skid, the force acting on the car is relatively constant, stays about the same the whole time. It doesn't matter if you're skidding along at 100 miles an hour or at 10 miles an hour. As you're skidding along, the stopping force is the same on the car the whole time, right? So would you agree then that the work done by stopping, by skidding, is just equal to whatever that force, that skidding force is, it stays the same times the length of the skid? Agreed? Okay, so it's linear, right? Okay, so let's look at a couple examples here. Let's say that you're traveling along at 20 meters per second. If you're traveling along at 20 meters per second, your kinetic energy, what's going to happen to your kinetic energy if you double it to 40 meters per second? Kinetic energy goes as 1/2 mv squared. So if I double the speed, it increases by a factor of what? 4. Okay. And yet you're only able to do work in stopping the car. You're only able to do work against the car at a constant rate, right? You lock up the wheels and the forces don't change, right? So that means that the stopping distance depends on what your initial kinetic energy is, right? If you double the kinetic energy, you're going to double the stopping distance because you have twice as much work to do to bring yourself to a stop, right? What's the danger there? Okay, how much further are you going to slide if you double your speed? 4 times as far, right? But our brain doesn't think that way. Our brain doesn't think that way because our brain hasn't evolved to think that way. Our brain thinks about, our brain has evolved to do things at our speed levels, right? When we've been running for millions of years, trying to throw spears and catch animals and things, we were always running where we can use our muscles to grab the ground. It's not really friction that's stopping us. It's our muscular forces, right? So we don't think of it in terms of, all I know is if I'm going really fast, I can stop pretty quickly by just pushing harder on the ground with my muscles, right? That's what I vary to change directions. Okay, we're not used to, it's not in our evolutionary repertoire to think about traveling 50 miles an hour or 80 miles an hour. That's way too fast, right? For us to think about stopping, we're always going to think about that in terms of a linear stopping distance. That's just the way our mind does the calculus, right? We don't think about it in terms of being 4 times as far. We think about it as being twice as far. And so when you go faster, you're much less likely to make the right calculations about, am I going to make that turn or not? Am I going to be able to stop in time or not, right? Does that make sense? And furthermore, where's that energy go if you do crash?
Into the other car.
Well, it goes into shared among your car and the other car or your car, but that energy's gotta be given up somehow, doesn't it? Right? Well, that's not good for you if you're the occupant of the car, right? See what I'm saying? It's gonna deform the metal, it's gonna do lots of things, but if you double your speed, you're increasing your kinetic energy by a factor of 4. You got 4 times as much energy to give up some way or another, right? Either you're gonna skid to a halt and heat up the road, or you're gonna crash all at once and you're gonna give up that energy in an awful big hurry, right? Explosively, right? So you get the idea? Yeah, cars are dangerous.
So just go slow.
Go slow. There you go. Exactly. Just go
Unless
slow.
someone-
Just go slow.
So let's see, you're riding on the wall.
8,000 pounds.
I'll be fine.
That's good.
I'm afraid. I'll just pick up my legs and the other car will just go underneath it.
You missed like 5.
Are there more questions?
Yeah.
We'll get them tomorrow. All right.